In this video, we're going to be discussing empirical formulas, which happen to be the primary application of percent compositions by mass. So an empirical formula is simply the form of a compound's chemical formula whenever it is expressed in lowest terms. This is easiest to see with organic compounds such as the five below. So for example, if we look at C2H4O2, we see that the number of carbon, hydrogen, and oxygen atoms is not expressed in lowest terms because 2, 4, and 2 have a greatest common factor of 2. So if we divide the number of carbon atoms by the greatest common factor, 2 divided by 2 is 1. 4 divided by 2 is 2, and 2 divided by 2 is 1. And now we see, if we write the formula as CH2O, there is no common factor that 1, 2, and 1 have other than 1. So this formula here is written in lowest terms. Likewise, C6H12O6, the greatest common factor is 6, and if we divide the number of each atom by the greatest common factor, you get the same formula. Likewise, C5H10O5, the greatest common factor is 5. If you do the same division, you end up with the same formula. Finally, C3H6O3, the greatest common factor between these number of atoms is 3, and if you divide the number of each atom by the greatest common factor again, you get the same formula. With CH2O, because there is no common factor other than 1, this formula is already in lowest terms, and therefore this is our empirical formula, or EF for short. In this example here, we can see how the concept of percent composition by mass can lead us to the discovery of an empirical formula. So in this case, we have an unknown compound and we're told what fraction of the compound is made up of carbon, hydrogen, and oxygen by mass, but we don't know what the chemical formula is. Now, if we wanted to compare the elements directly, we can't use mass for direct comparison because carbon, hydrogen, and oxygen have different molar masses. So in order to compare the three elements directly, we need to use moles. And the first thing to do in that case is to find out what the molar masses of carbon, hydrogen, and oxygen are so that we can convert mass into moles. So let's double check our periodic table. Molar mass of carbon is 12.01 grams per mole, oxygen is 16 grams per mole, and hydrogen is 1.01 grams per mole. So if we start by converting carbon's mass into moles, 8.4 grams of carbon times, and if we want to convert grams into moles, we need to put 1 mole in the numerator, and the molar mass of carbon, 12.01 grams, in the denominator, so grams cancel, leaving us with moles of carbon. If you put this into your calculator, this comes to approximately 0.6994 moles of carbon. Next, let's try the same thing with hydrogen, 2.1 grams of hydrogen. And again, we want to cancel grams and convert to moles, so we're going to multiply by 1 mole over the molar mass of hydrogen, 1.01 grams. So if you put this into your calculator, this number comes to approximately 2.079 moles of hydrogen. Finally, if we do this with oxygen, 5.6 grams of oxygen times 1 mole over the molar mass of oxygen, which is 16.00 grams. Put this into your calculator, and this, fortunately, comes out to exactly 0.3500 moles of oxygen. You will notice that I'm not keeping the same number of significant digits for my moles as I am with the mass. That's because the number of significant digits in empirical formula calculations does not actually matter, and you'll see why as we figure this out. Now, what exactly can we do with the number of moles of each element? Well, again, these decimal numbers don't really make a lot of sense, but what we can do is we can look for the element that has the smallest number of moles, which in this case is oxygen. Oxygen has a smaller number of moles in the compound than hydrogen or of carbon, and we're going to use this as a benchmark. So if we take the number of moles of oxygen and divide it by itself, I won't insult your intelligence, but this comes out to 1, because whenever you divide a number by itself, it comes out to 1. So what we're doing when we do this is we're saying that oxygen is our benchmark for comparison. So we don't have 1 mole of oxygen, but this is saying if we had 1 mole of oxygen, how many moles of the other 2 elements would we have? And we can figure that out simply by dividing the number of moles of carbon by the number of moles of oxygen and the number of moles of hydrogen by the number of moles of oxygen. And if we do this, the results are fairly interesting. So if we take moles of carbon, divide by moles of oxygen, this is going to come to, again, approximately 0.6994 moles of carbon divide by 0.3500 moles of oxygen. And if you put this into your calculator, this comes out to approximately 1.998, 1.99 repeating. We can then round up and say that this is approximately 2. So what this means is that if we had 1 mole of oxygen within this compound, let me rewrite this quickly, CHO, approximately 1 mole of oxygen, what this ratio tells us is that we would have 2 moles of carbon for every 1 mole of oxygen, and slowly our formula begins to take shape. We can do this same calculation with hydrogen here. So again, 2.079 moles of hydrogen, and we're going to divide that by our moles of oxygen, 0.3500 moles of oxygen. And if you put this into your calculator, this comes to approximately 5.94. Again, 5.9. I think we can safely round this up to 6. So again, what this is telling us is that if we had 1 mole of oxygen in our compound, that would correspond to 6 moles of hydrogen. And using that, we have successfully found our empirical formula and discovered this compound that we did not know existed. However, in certain situations like this, you may not necessarily be given a mass number and instead can simply be given the percent compositions by mass. So how do we determine the empirical formula if you're not actually given mass numbers? The simple answer, you cheat. We know that the total of these percentages is going to be 100%. And we know that these are percent compositions by mass. So the way that we cheat is we say we're not looking at percentages at all. We're looking at a 100-gram sample. And because these are percentages, if our sample's total mass was 100 grams, each of these percentages would correspond to a mass in grams, and we can solve the question exactly the same way. So let's start with carbon, 47.37 grams of carbon. We need to convert to moles, so we multiply by 1 mole over the molar mass of carbon, 12.01 grams. Grams cancel, and if you put this into your calculator, this number comes to approximately 3.944 moles of carbon. Again, significant digits don't matter. I will explain why clearly after this calculation is done. Next, let's move on to hydrogen. 10.59 grams of hydrogen multiplied by 1 mole over the molar mass of hydrogen, 1.01 grams. Grams cancel. Put this into your calculator, and this comes to approximately 10.49 moles of hydrogen. We have 1 element left. Let's figure out the number of moles of oxygen. So 42.04 grams of oxygen, which we multiply by 1 mole over the molar mass of oxygen, 16.00 grams per mole. Put this into your calculator, and this comes to exactly 2.6275 moles of oxygen. So once again, these individual numbers don't exactly tell us much until we begin comparing them to each other. So let's look for which mole number is the smallest. That turns out to be oxygen yet again. So we know that oxygen is going to be our benchmark. So if we take moles of oxygen and divide it by itself, we get 1. So again, this assumption is that if we have 1 mole of oxygen within this, how many moles of carbon and of hydrogen would we have relative to that? So first, let's compare our moles of carbon with our moles of oxygen. So let's take 3.944 and divide by our amount of oxygen, 2.6275. And if you put this into your calculator, the results become a little bit interesting. They actually come to approximately 1.5. So what exactly do we do here? Because we can round this up to 2, or we can round it down to 1. Well, which one do we do? Let's put that on hold and let's figure out hydrogen first. So if we compare our moles of hydrogen to our moles of oxygen, we're going to take 10.49 moles of hydrogen, and we're going to divide by 2.6275 moles of oxygen. If you put this into your calculator, this comes to approximately 3.992, which again, 3.99, it's fair to say that we can round that up to 4. So in this case, what we figured out is that if we have 1 mole of oxygen in this compound, that would correspond to 4 moles of hydrogen. But what exactly do we do with this 1.5? We know it's possible that you can't have 1.5 carbon atoms here, but if we round this up to 2, then our ratio would change. And if we round this down to 1, same thing. So what can we do with our empirical formula that keeps the ratio of carbon to hydrogen to oxygen the same while making this number whole? Well, if we take the whole empirical formula and multiply it by 2, we know that 1.5 times 2 is 3. We know that 2 times 4 is 8. And we know that 1 times 2 is 2. And we know that we still have an empirical formula here because 2, 3, and 8 do not have a common factor other than 1. All of these numbers are whole, which means that the number of atoms makes sense, and we haven't changed the ratio of carbon to hydrogen to oxygen that we found in our calculations. So what we've just discovered here is that sometimes the mole ratios between atoms do not come exactly close to a whole number, but if the mole ratios come to specific decimal numbers, we can multiply them in the following ways in order to produce a whole number. So as we've seen, this number was 1.5, and if we multiply this by 2, it gives us a whole number. If our number ends in 0.333 or 0.666, these are multiples of 3. So if we multiply them by 3, it would give us a whole number. If we have a number that looks like 0.25 or 0.75, well, if we multiply these by 4, they will come out to whole numbers. And if you have numbers that end in 0.2, 0.4, 0.6, or 0.8, if you multiply them by 5, then these should come out to be whole numbers as well. In the next video, we're going to look at the second part of determining chemical formulas. Once you have an empirical formula, the ability to determine molecular formulas.